So my research is using machine learning aggregated remote sensing data for wildfire occurrence prediction and feature selection. And I chose case study in California because that is where I'm from, California. And so first, let's address the issue of why we should study wildfires. So due to climate change, wildfires are becoming increasingly frequent and destructive on a global scale. From California, recorded wildfires alone have ravaged more than 2.5 million acres of land in 2021. And in Figure 1, we can see an upward trend in the acres burned by wildfires over time. And this is especially a problem because wildfires pose a serious challenge across a variety of spheres. Some of these include environmental consequences, which include releasing greenhouse gases, exacerbating climate change, and endangering wildlife and biodiversity, as well as human consequences such as injuries and fatalities, air pollution, as well as destruction of agricultural land. Finally, there are a lot of economic consequences, such as destruction of private property and assets, destruction of public land and infrastructure, and finally, suppression costs and costs up to billions. And one important thing I want to highlight here is that wildfires exacerbate. Let me see if I can zoom in my poster actually. Not sure if it's okay. If I have to do this. Can you guys see my poster? Or should I reshare my screen?
Yes. So okay. When you are walking through your presentation, it's better that you point out where you are presenting. So
okay, gotcha. All right, I think this might be easier. I just do this. Cool. Okay, so I was right here. And so one important thing to highlight here is because wildfires release greenhouse gases, this actually exacerbates climate change, which then goes back and increases wildfires by causing unpredictable climate conditions. So essentially, there's a negative feedback loop that results in an increase in both wildfires and climate change. And so that's why it's very devastating. And actually, United Nations recently published a paper talking about how wildfire is going to be one of the biggest issues that we address in the coming decade. It's going to be wildfire crisis, as they put it. So essentially, it's a very important issue to address. However, the good news is that recently, the increasing availability of remote sensing data and advancements in machine learning have provided an unprecedented opportunity to tackle this challenge. And so one prior study used remotely sensed data to predict fire risk ratings in Cambodia. And another one achieved 94.5% predictive accuracy employing the bagging decision tree classifier. And so a wide range of different features have been employed in this emerging field of remote sensing data-driven machine learning research. And in the histogram below, I took a sample of 10 papers and essentially graphed out their features. And so as you can see, there's a wide range of features, and the largest column is others, because there are so many features, I couldn't include all of them on here. But essentially, as you can see, there's a very large amount of features. And so from this observation, essentially leads to the need to identify the most relevant features, because there's such a large range of features, which ones are actually important, which ones are actually most relevant for machine learning, right? And so this actually remains elusive, and in addition, a comprehensive feature importance ranking as well as an optimal feature subset selection has not been satisfied. And so let's define some terms here. First, what is a feature importance ranking? So feature importance is essentially how important a feature is towards a machine learning classifier, and so that is going to be how effective the feature is in producing the in affecting the dependent variable, which is going to be whether or not there is a wildfire. And the feature subset is going to be a subset of the wider range of features that actually, number one, produces the best result, where result is defined as the highest score in whatever metric we use to evaluate our model, as well as reducing the time for data collection, because we don't have to collect data for a smaller subset of all the features. So essentially, these are the three relevant knowledge gaps addressed in these features. Number one is identifying the relevant features. Number two is ranking the features by their importance. Number three is actually finding the optimal feature subsets. Okay, so how do we do this? Well, there are actually 5 steps. So first, we have to identify the relevant features. And to do this, I went through a comprehensive review of previous studies and essentially categorized the features I found in 4 categories. These include meteorological features, landscape features, vegetation, as well as human/others. So meteorological features include temperature, wind speed, humidity, precipitation, radiation, as well as vapor pressure deficit. And these are mostly collected from NASA. Landscape include moisture, land cover, soil wetness, elevation, droughts. Vegetation include NDVI, vegetation type, as well as other vegetation measurements. So NDVI is a very popular feature used in a lot of papers, and that is essentially a measure of how dry the land is, measured by the vegetation. And finally, there's human/other features, which include distance to road, population density, nearby settlement information, which include population density, etc., surface roughness, as well as daylight duration. So onto data collection, and this is the part that actually takes the most time. So first, we have to acquire data sets to train and evaluate our machine learning model on. And so 2.1 is fire occurrence data. So this is acquiring the yes fire data, and to do this we use I use NASA's fire information for resource management system, and essentially I acquired all data from USA and trimmed the data down to the time period 2015-2021 in location which is California, and then I collected non-fire data using Modus, utilizing Google Earth Engine. So essentially, I use Google Earth Engine's API to query Modus data, which is a very large data set that I can just download and use directly. And then from this, I randomly generated longitude, longitude, daytime tuples, and selected only non-fire high confidence line pixels. And so this essentially yielded 10,000 no-fire entries, and again from 2.1 we obtained 10,000 yes fire entries, and these are all delineated by spatial temporal parameters, which are latitude, longitude, and daytime. 2.3 is features collection. This is by far the longest part of the entire research, because for each of the 104 relevant features, I had to go through 20,000 different rows, and each individual query takes like 2 or 3 seconds because it has to use the API. So essentially this part takes a long time, and I utilize the cloud computer to do this. And so essentially data for all relevant features were collected for every entry, and the flowchart on the right demonstrates the process. I'm not going to go through every single part of it, but a couple of points to highlight. So to use the US Census data, I first have to use reverse geoencoding, which essentially turns longitude, latitude into a zip code, and then from that zip code, I'm able to obtain relevant information, including population, etc. And then also NASA series, that's used for solar radiation. Gridment I use to obtain a lot of drought data. And Modus is actually my largest data source, even though it's like pretty small in this flowchart. It's definitely, I'd say like 50% of the data came from Modus, and Google Earth Engine has really reliable and easy to use API, has a really easy to use and reliable API to query Modus data. And so essentially, and also another huge part of this is NASA Powers, and that's essentially a data set an API provided by NASA to query a lot of meteorological data. And so this includes like temperature, etc. And the good thing about NASA Powers is that they actually provide a lot of different types for each parameter. So for example, for temperature, they provide temperature at 2 meters, temperature at 10 meters, temperature max, temperature min, temperature average, etc. Okay, and also I collected these features based on querying from the latitude, longitude, daytime tuple. Okay, so the next part is data processing. And so because like the results from feature collection included a variety of different data sets, a lot of them had different like resolutions. How do you combine these, right? So first we corrected spatial resolution to 1000 meter by 1000 meter using a pixel pyramid technique. And this is inspired by Google Earth Engine because that's how they deal with different resolutions. And temporal resolution was corrected daily by extrapolating most recent available data from at least 1 day before each daytime entry. So essentially what I did was I found out if there was data for for T-1, which is the time, 1 day before the time, and then if there's not, I keep going backwards until there is a time. And so 3.2 is data cleaning and normalization. And so first I removed entries with all NaN values or bad pixel data. So this includes outliers. And then I applied one-hot coding on land/vegetation cover types. So for example, there are like 13 different vegetation cover types. And so instead of having the numbers be from 1 to 13, I had 13 separate columns and a 0/1 indicating whether or not each entry is like one of the vegetation types. And finally, I normalize feature columns. So via the z-score. So essentially, this is going to be the difference from the mean divided by the standard deviation of the column, and it's a pretty standard way of normalizing data used by I think standard scalar and a lot of other algorithms in machine learning. And the final data set after data cleaning, normalization, etc., included around 16,000 fire occurrence / non-occurrence entries, each having 104 features spanning multiple categories. So which are these categories? And essentially, this provided the data set I need to train my machine learning model. And so number 4 is machine model testing and evaluation. So I employed an 80-20 test train split and used F-score as the model evaluation metric because it essentially is a harmonic mean between precision and recall, and both are important for natural disaster prediction. And also tested 14 different machine learning classifiers, including logistic regression, decision trees, which are related to random forest, bag decision trees, naive Bayes, support vector machines, ADA boost, XGBoost, KNN, etc. And so essentially, these are pretty easy to test because I can just use sklearn. Essentially, after the model testing, I selected the higher scoring model, XGBoost, as the base model in the next steps. And the next steps are feature importance and selection. And so in 5.1, I first dealt with feature importance. And so here I employed 4 different feature importance algorithms. These are permutation feature importance, drop column feature importance, SHAP, and adherence model explainers. So permutation feature importance and drop column are pretty similar. Essentially, I randomly perturb one column of the data and measure the impact of that perturbation on the overall model score. And based on that, I calculate the feature score in terms of how effective it is in how effective it is in the SOAR. And then SHAP is actually a black box this method. Essentially, there's a library very useful that you can use directly, and it's based on cooperative game theory. And actually, I cited it here. It's developed by some researchers, and it's an interpretive way of explaining features. And the feature score is actually based on the Shapley value. And finally, I use inherence model explainers. So for example, feature coefficients in logistic regression and Gini indices in decision trees. And so the score features here are based on internal model measures, metrics. And so finally, after going through each of the 4 algorithms, I standardized feature scores and aggregated the results to compute final feature scores. So last step is feature selection. And here I implemented a feature selection algorithm based on the randomized simulated annealing metaheuristic. So a metaheuristic is essentially a generalized heuristic to solve some optimization problem. And so in our case, it's optimizing the state, which is essentially what features to include and what features to exclude. And so the metaheuristic here is to accept the worst state with decreased probability to increase the chance of reaching the global maximum state. And so down here, I explain what state is. State is going to be the feature subset mask, indicating inclusion or exclusion. The score of a state is going to be the F score based on the base model, as established up here. And so essentially, we're trying to maximize the state score. And I'm not going to go through each step, but essentially, after running the algorithm a lot of times, I ran it for, I think, for an hour or so, I was able to obtain the final feature subsets. Okay, so the final sum z-score for all features were computed proportional to the relative importances in machine learning models. The top features shed light on the most important driving factors behind wildfires and serve as a starting point for future research investigating wildfire causes. Additionally, the ranking of these features provide essential decision support for improved wildfire preparedness and response. And so here's a ranking. Here's the top 10 most important features, which are soil moisture, vegetation index, minimum vapor deficits, latitude, surface roughness, standard precipitation, longitude, wind speed at 10 meters, soil radiation, and dead fuel moisture. And these are all collected from a variety of sources, as down here. And in addition, a lot of these have been discovered in previous research. For example, soil moisture is a very popular one that is often very used widely in a lot of cross-summer research. But other ones, like for example, minimum vapor deficit is not used as widely. This is actually I've only found I think 2 papers which actually use this, so that's pretty interesting. Yeah. And so an optimal subset of 15 features were selected from the full list of over 104 using a novel implementation of the simulated annealing feature selection algorithm. And that is the selection algorithm down here. And so feature models and machine learning wildfire prediction research could directly utilize the subsets and the data collection pipeline established in this research to significantly reduce data collection efforts. And the 15 features are actually right here. And on closer examination, a lot of these features are similar to the top 10 most important features. However, there are some differences because in order to optimize the latent interactions between features, it's not necessary to include a lot of features because a lot of them can be are closely related to another feature. And so finally, utilizing the highest scoring model, XGBoost, along with the optimal feature subset, yielded the final F-score of 95.98. And again, F-score is going to be the harmonic mean between precision and recall. And so this is pretty high. This machine learning classifier can be utilized by the California Department of Forestry and Fire Protection for wildfire prediction to take preventive measures. And the confusion matrix from XGBoost is shown below. The full list of 104 compiled features and the final complete source code in Python are made available through this research, including a full implementation of the simulated annealing feature selection algorithm and all parts of the data collection pipeline. And finally, I would like to acknowledge NASA, Google Earth Engine, and Rapidamic Labs for support and mentorship. Thank you.
Thank you so much, Timothy.